All right. Let's go over exponential functions because we need to know those to do the logarithmic functions. So exponential functions have this form. Where A is positive and A does not equal 1. X can be anything. So if A is greater than 1, let's say A is 2. The graph looks like this. And it always crosses at 1 on the y-axis. Why does it always cross at 1? Because at this point, 2 to the power 0 is 1. If A is a fraction or a decimal, less than 1. Again, it still crosses through 1, but it's a decreasing function. Now, let me show you why it's a decreasing function. You notice we have no x-intercepts. The function, the straight up function cannot be negative. It's always going to be above 0. So if our base is greater than 1, the negative exponent simply means that it's a reciprocal. It's still going to be positive, but it's going to be small. It's going to be 1 over 4. At 2 to the power negative 1, that negative exponent simply means move it to the bottom. This becomes just 1 over 2, so it gets bigger. Anything to the 0 power is 1. And then for positive integers, exponents, we get that. So the bigger the negative value is, the smaller the number becomes. That's why it goes closer to 0 on these, on the negatives, and greater on the positives. And it's just the opposite on the other side. Well, it's not the opposite, it's the same thing. But you notice what happens here. This number here is 2 over 1, right? Because it's a negative exponent, I flip it. The same thing happens here. If I have 1/2 and I raise it to the power negative 2, all that does is flip what's inside the parenthesis and changes the sign to positive. So it's 2 squared over 1, which is 4. 1 over 2 to the power negative 1 is 2 over 1 to the power 1, which is 2. Anything to the power 0 is always 1. 1/2 to the power 1 is 1/2, so it starts getting smaller. And 1/2 to the power 2 is 1 squared over 2 squared, which is 1/4. It is. And that's what happens because with the negative exponents and positive exponents, it flips it. That's why in this one, it's a decreasing function. And in this one, it's an increasing function. So that's a review of exponential functions. That's what we did last time. Exponentials and logarithms are inverses of each other. Are inverse functions of each other. Do you remember how we tested that? If they're inverse functions of each other? It's how we started this chapter. The fog and Goff. Yeah, the composite. The G of F of a G, right. No, X has to equal X. Right. So inverse functions have to satisfy this condition. So they have to satisfy that condition. But the question is, how do we solve for X if it's the exponent? If it is the exponent. This is where logarithms come in. We use logarithms. So let's find the inverse of this. First step is what? Change X and Y. Now we got to solve for Y. Back to the problem. What we do here is we'll take the log base 2 of both sides. It'll make a lot more sense when I go through it all. So what happens here is on the left side, we just have log base 2 of X. These two cancel, gives us our Y value. So the inverse of Y is equal to that. We'll go through the properties. I like to go through they save the properties for the third or fourth chapter or section, which is ridiculous. We should start off with the properties to begin with. Let's talk about logarithms. This is how it's written. How do you read it? It is read the log base A, that's the base, of X. That's how you'd read it. Remember when we talked about exponents? What was A called here? It's also called the base. So it's not by accident or happenstance. It's designed that way because A will always be the base. Whatever's down here will always be the base. We have three types. We have three types of logarithms. They depend on the base. If it's base 10, if it's base E, or any other base. So if we have a log base 10, our numeric system is base what? Our counting system is base what? Or base 10. If we have 10 fingers, everything's in base 10. So if it's base 10, we call this a common log. If it's a common log, we don't have to write the base. If there's no base, if there's nothing in there, it's automatically a base 10. It's a common log. If it's base E, we call that a natural log. Because that's what we use in biology and chemistry. It happens in nature. We log base E are, well, it's a natural log. We do all our calculations with that. So it's a log base E. So if we have a log base E, remember E is a constant. We talked about last class. What is E value? 2.1718128. Yeah, so it's a constant. If you have a log base E, it's called a natural log, and we just write it as ln x. If you see a log with nothing there, it's log base 10. If you see an ln, it's log base E. Anything else has to be written there. Any other number, any other base has to be written there. Your calculators only use these two. If you look at your calculators, you only see logs or ln's. You don't see anything else. There's no log base, whatever. So we have to use a conversion for these. And we'll talk about that in a little bit. Well, I'll show it to you now. To convert log base A to either ln x or log, or no, to convert the log base A, whatever A is, x, to either natural log or common log, here's the conversion. Let's do ln first. So take the ln of the operation, ln x, over the ln of the base. If you don't want to use common logs, you can write common log x, common log a. You notice the base is always on the bottom and the x operation is always on top. The base is on the bottom. It's the ratio we're interested in, and that tells us the value. So if I give you this equation, log base 3 of 5, you couldn't do it on your calculator, so how would you convert it? Yep. Or you could use what else? ln5 over ln3, right? Either one, doesn't matter which one you use. They're both going to give you the same answers. But now you can use calculators. This is the part that we need, the conversion from a log to an exponential and vice versa. I mean, if you do it one way, you do it the other way. Log base a of x is equal to. Here's a process. So it equals some number y. Let's say it equals some number y. The conversion is the base has to remain the base. So it comes over here and pushes up that answer. Since the base is gone, the log drops away and we get x. There's your conversion. Solve for x. Oh, there. What'd you get? Which is what? Yes. So here we have a conversion. 2 to the power 3. The log drops off equals x. 2 to the power 3 is 8. So now we know what x is. That's all there is to it. Well, that's kind of. Let's look at some examples here. Example 2. A. We have log base 10 of 10,000. Find each of the following logs. What is this equal to? Nope. Well, it does. Yeah. Okay. Yeah. It does equal log 10,000, but what is that value? What's the answer? Do we know what it is? We don't know. So we're looking for x. We're looking for some value. Convert it. This is 10 to the power x equals 10,000. So we have 10 to the power x Can we write this number as a base 10 number? 10 to the power what? How many zeros does it have? So since the bases are the same, then x has to equal 4. There's your answer. That's what I'm looking for. Solve this one. Since we don't know what it equals, let's say it equals some number x. What's the base? It's base 10. So it pushes that up. So we have 10 to the power x is equal to 0.01. How can we rewrite this one? This is the same as 10 to the power -2. Since the bases are the same, compare the exponents. So x equals -2. Log base 2 of 8. What does that equal? All right, we don't know what it equals. So put x there. The power pushes up the x, so we have 2 to the power x equals 8. So we're looking for a number base 2. So what is 8 made up of? 2 times 4. So 2 to the power x is the same as 2 to the power 3. Since the bases are the same, the exponents have to be the same. X equals 3. Let's look at D. Log base 9 of 3. All right. We don't know what it equals. So the 9, we have 9 to the power x is equal to 3. We have to get common bases. So 9 is made up of what? So it's 3 squared. If power to a power, so you multiply, so it equals 2x equals 3. 3 to the power 1. Since the bases are the same, the exponents have to be equal. So x is equal to 1/2. log base 6 of 1. The next two are going to be properties, actually. It's going to be what?
I was like,
Yeah.
I was like,
6 to the power x is equal to 1. The only way that can be is if x is equal to 0. Anything to the 0 power is 1. This is our first property, and we'll get to another one here. F log base 8 of 8 equals what? Since A equals some number x, 8 pushes up the x and drops. So 8 has a power 1, so x is equal to 1. Which brings us to our first two properties. Property 1 and property 2. Log base A of 1 is always 0. So ln of 1 is 0. Log of 1 is 0. If there's a 1 there, it has to be 0. Then if the base and the operation are the same, it equals 1. So natural common log of 10 is equal to 1. Ln of E is equal to 1. Those are our first properties. So if they're the same, the base and the operation are the same, it's 1. If it's an operation of 1, doesn't matter what the base is, it's 0. What does the graph of a natural log look like? Since the graph of a exponential function looks like this, what does the graph of a logarithm look like? This crosses at 1. Remember, okay, this location here is 0, 1. What do you do to find the inverse? Switch the x and y. So it's going to be 1, 0. And remember, how are inverses graphed? Along the 45-degree angle line. So here's a 45-degree angle line, y equals x. So the natural log, or the logarithm, looks like this, while the exponential looks like this. So the domain of your exponential function, what does the x values go? From what to what? Very good. All real numbers. Yes. What's the range of an exponential function? Has to be greater than 0. There's no x-intercept. It goes infinitely close to it and never touches. This is the y-axis. Look at the log. What's the domain of the log? This is the log. This is the exponential. 0 to infinity. It's to the right. In other words, you cannot put a negative number inside log, or you cannot put log of 0. Doesn't exist. And what's the domain? Or what's the range, I mean? Yeah, they're opposites of each other. They're inverses, so they're opposites. The domain of the exponential is the range of the log. The range of the exponential is the domain of the log. Example 3. Convert. If I give you 16 equals 2 to the power x, if I give you 10 to the power -3 equals 0.001, and if I give you e to the x equals 70, convert these to logarithms. You have to flip that. Remember, what's the 2 represent? That's the base. So we're going to have a log base 2. And you switch the x and y. So the next one is log base 10. Yeah, it's going to be, once you write that down, then it's going to be, so the answer is going to be log of 0.001 equals -3. And the last one, if you have a hard time with these, think of the conversion. The a pushes up the y equals x. This is the conversion rule. Example 4, convert to exponentials. Log base 2 of 35 or 32 equals 5. Log base a of q equals 8. X equals log base t of m. What's the first one? Mm-hmm. 2 to the 5th power equals 32. Next one. And the last one. T to the power x equals m. Right. It's just, once you see the pattern, it is super easy. Example 5 deals with a calculator. on how you'd put in the calculator. If you did the first one, it's gonna give you some number. It's 10 to the power, let's see, it's 100,000. Ten to the fifth. Point something. So just type it in the calculator. So type in this number, hit log, and there you have it. This one's gonna give you a negative answer. This will give you a pretty large positive. This will give you a pretty small negative. So type in 0.0000239, hit log, and it'll tell you some negative number. How about the last one? You type it in there, it'll say error. Where's your calculator? Because remember, X cannot be negative.
So if we had like an equation like that.
No error, no solution. This is when we say, when we have this kind of things, I want you to practice too, is try to get as much practice as you can while you're in here with me. It's because the second you walk out the door, I mean, you're gonna forget everything I talked about. Natural logs. Okay, all these on a calculator.
So the natural log is like the.
LN.
The N.
Yeah, the LN, yeah. No, not the N by itself, it's the LN. Let me show you here. I'll show you how it. Go to scientific. It's this one down here.
Yeah, so this.
Yes. It's the LN. Just type that. Just type in the number and hit LN and you'll get it. So this one will be positive. This one's gonna be negative. C does not exist. What's D gonna equal? 1, because log base E of E is 1, and E is log base E of 1 is equal to 0. But again, I need you guys to practice that and see that. And it also gives you the shortcuts here. We talked about the change of bases already. So find log base 5 of 8. Example 7. Find log base 5 of 8. Seven says using common logs. In example 8, let's use natural logs. So the first one is going to be what? Log 8 over log 5, which is equal to what? Use your calculators. Get your calculator out, your cell phone. Well, I just talked to you about that.
Yeah.
Get your cell phone out and start doing this stuff. Even your cell phone should have a scientific calculator on it. And do the same thing with the next one with LN8 over ln 5 and see what you get as an answer there. Well, it's going to be, it's the ratio of the two. The answer equals what?
296.
That.
Okay,
Yeah, and it'll tell you how many decimal places to put the answer down.
I was like, oh.
Whatever that is. Example 9. Graph y equals log base 5 of x. You'll have to plot some points on the computer because you'll have, we know the y, the x-intercept. Where's the x-intercept? 1. It's always going to be 1 unless there's a horizontal or vertical shift. The graph looks something like this. But you'll have to plot some points to get the exact graph on the computer. So you'll have to plug in some values of x, do the log of x over log of 5 and get the value. But it's going to look that way. Example 10 now deals with transformations. A, f of x equals ln x plus 3. What is that one going to look like? What kind of shift is it? Horizontal because it happens inside the function. So we know the original function looks something like this. Which direction and how many spaces does it move? Yeah, so this origin moves to the left 3. So there's your new origin at -3. It crosses at there. So it shifts back 3 spaces. This will get B. F of x equals 3 minus 1/2 ln x. So let's look at the transformations that are happening here. What's the original function we're graphing? Ln x. It looks like this. What's the next thing it does? Well, let's just build out. 1/2 ln x makes it do what? It makes all the y values half as much. So if this was 1, it's now a half. It's compression, right? It's a vertical compression. Because whatever ln is, let's say it's 4 divided by 2, there's your new y value. The third shift we do is now it changes to negative. What does that make it do? X-axis, because it now changes all the y values to negative and all the negative y values to positive. So it looks like this. It's gonna be real short. And then what does it do? Then it goes up 3 spaces, right? So that used to be the origin. Now I go up 3 spaces. There's my new origin. My graph now looks like this. It goes up 3 spaces. Pretty straightforward. Again, once you understand what the graph looks like and what transformations we did in chapter 2, then it should be pretty straightforward. That's if you've completed chapter 2 already. Walking speed. In a study by psychologist Borenstein, it was found that the average walking speed W in feet per second of a person living in a city population P, the walking average of the population, is given by 0.37 ln plus 0.05. In a populations of Billing, Montana, the population is 106,954. Find the average walking speed of the person living in Billings. All it's telling us to do is put 106.954 into our equation. So the ln of 106.954 plus 0.05. And we'll do the same thing with B. So 106.954 ln times 0.37 plus 0.05. So its average walking speed is 4.33 miles per hour. Two, 7, 1, 4. And you notice how I'm doing it? I'm doing the ln first so that I don't get the numbers mixed up with the first number I put in there. So the ln of 2 million is that. So then I take that value, multiply it by 0.37. That gives me that answer. And then I add my 0.05, which is 5.53 miles per hour. So the bigger the city, the faster you got to walk, which is contradictory because it's more crowded. You can't walk that fast. And likewise, example 13 is just plug in the values of the Richter scale, and that'll give you the same answer. Give you an answer. So for example 13, we're doing the Richter scale is the log of I over IO. Ten to the power 9 times IO over IO equals log of 10 to the power 9, which is 9.0 Richter scale. It said the undersea Tohoku earthquake and tsunami near the northeast coast of Honshu, Japan on March 11, 2011 had the intensity of 10.9 times I to the 0. That's the intensity of that earthquake. So plug that into the formula, divided by I sub 0, those cancel. So log base 10 of log of 10 to the base sat. Here's another property. So if we had log base 10 of 10 to the 9, you can't have exponents in logs. So the exponents go out in front. Log base 10 of 10 is the same thing as 1. So that's another property. If you have an exponent, then that exponent goes out in front. All right, that does it for that section.